Hi everyone. My name is Jim. I'm going to talk about serverless machine learning in Python. And I'm going to talk about one of my passions, which is surfing, and a project I've worked on, which is predicting the surf height at a beach in Ireland. And this is a Java-centric conference, so this is, I think, the only Python talk today. But the system was originally built in Java. We'll get to that. So I'm going to talk about how you build production machine learning systems, what I call prediction services. So we're not going to just train models. And if you've ever done a course in machine learning, you'll end up doing something like this. You get some pretty static data. You create some features, train a model, evaluate it, and you're done. So a real-world system will have new data always coming in. The data is not static. And what I'm going to talk about is how we can break up this monolithic ML pipeline at the start into three parts. Feature pipeline to create our features. It can run on its own schedule. A training pipeline to create your models, and that can run on demand. It doesn't necessarily need to run on a schedule. And then a prediction pipeline, or a inference, in this case a batch inference pipeline, and again it'll run on a schedule. And just when I say run on a schedule, if we think of the surfing example, I get some wave data every day, so from one source every 24 hours and another source every 6 hours. So this program needs to run every 6 hours for the data that we're going to use to predict the swell heights, and then every 24 hours from beach data. And then make predictions. I'll run that once a day, but I could run every 6 hours. So that's what it means by serverless. It's going to be a program that runs without me having to install any infrastructure. I don't have to monitor or manage any infrastructure. And most interesting, it's all going to be run on free platforms. So the problem I'm going to describe is surfing. It's predicting the height of a wave at a beach. And I actually wrote a paper about this way back, published at the top machine learning conference called ICML. And what it does is it takes in predictions of what we call the swell in the open ocean. So off the coast of Ireland, the Americans have these buoys or buoys, and they give predictions of the height of the swell, the direction of the swell, and the period of the swells, the time between waves. And you can correlate that with the height of a wave at the beach by getting observations from the beach. So we get both of those. And the problem looks like the following. You can see here, we've got this point break. We go back here. We've got a point break coming in from the top. There's a swell coming in. It hits the point and it rises up. And then on the beach, you can see it refracts around the headland. And the waves are much lower at the beach than they will be at the headland. So it's not a trivial prediction problem to solve. You need to know all of these three features at least to get good predictions. Now, what I'm going to show you concretely is the system. Now, we originally wrote this system in Java back in 2004. It went out to the internet. It went to this website called La Hinch, where we got the observations of the beach, of the height of the waves at the beach. And then NOAA, who are the Americans, the North American Observation and I think it's Atmospheric Administration, they produced the predictions of the height of the open ocean swells. So the Java program went out, scraped the data, we wrote the data to a MySQL database, and then we had a PHP front end to visualize it. I think it was about 8,000 lines of code. So I rewrote the entire system in Python this year because I thought it was cool, and we had this system called Hopsworks, which would give you serverless store for your features and your models. And you just need to register to create an account. If you want to follow along, by the way, if you have a laptop, you can probably do it in the time I'm talking here. The only thing, if you have a GitHub account, you need to use your GitHub account, because we're going to use that to, you can see on the left-hand side, we're going to have some serverless compute. We're going to use GitHub Actions for the serverless compute. We're going to store the state in Hopsworks. You need to create an account there. And then we're going to use GitHub Pages for the user interface. I'll just show you what it looks like to give you the feel of it. Right? So this is the GitHub page here. And if you go to it here, it's called CJSurf. And you can see here there's a couple of badges. These are our GitHub Action badges. They tell us that they're passing. This is the actual beach here in Ireland. You can see that's where Ireland is, and that's what it looks like. And then the actual system just produces this graph. It's nothing too fancy. It's called GitHub Pages. GitHub Pages is it's a HTML or a Markdown page you can associate with a repo in GitHub. And it basically draws this. So I can see, for example, at the weekend on Saturday, it looks pretty good, 4 foot, which is very high waves. That's going to be overhead. Then Sunday doesn't look too good, 1 foot, which is about this high. So that's basically it as a service. And what it's doing is it's running in the background. I'm not paying to run this. So the reason why we didn't continue with the original Java PHP system was it cost $120 a year, and we didn't have that money. But this thing runs for free. So let's have a look at the actual architecture of it. So the way it's going to work is it's actually only 4 programs in total, and they're all notebooks. So if you're familiar with Python and you've used notebooks, you don't even need to rewrite it in Python code to productionize your code. We can run these notebooks using something called mbconvert. So there's 2 notebooks here that pull down the data from the 2 different sources. So we get the height of the waves at the beach from this Lahinch. So this is the surf report features notebook. We've got another notebook called swell features, which is going to go out to the American website and grab the predictions of the swell heights. And then we have another notebook which will train our model with the features that have been written here. So these first 2 notebooks will write the features to the feature store. And then our training notebook can pull down those features, create a model, and write it back to the platform. So then when we need to make predictions, we have a different notebook, which is basically going to download the model, download the features, make the predictions, write those back here so that we can analyze the performance of the system, but also it's going to just save an image. This image we saw, the graph showing us the prediction of the wave heights, it's going to save it to GitHub Pages. That's the system, right? Now, there are loads of examples of serverless machine learning systems out there. I saw a really cool one this week, which was using GitHub Actions. Again, it was you'd upload your video. Basically, you'd create an issue on the GitHub page, and you put in a URL to your video. And what this GitHub Action would do would download that video, run it through a system developed by OpenAI to generate the captions, so the actual words that were spoken, and then translate them into English. So they were using this for the Ukraine war to get a lot of the Russian propaganda and translate it into English. It's kind of cool. So that's basically it, and this is what we're going to look through. Now I'll go through it in code. We'll start with we'll have a look at some of the different parts here, but basically we'll start here by getting the observations of the beach heights. That's a notebook, and it can run in one of 2 modes. So one is backfill. I still have that data from 2004, so it's a CSV file that's in the GitHub repo. I can load that up, create some features, so I have some initial training data to train my model with, and then when we want to go out every day, it should go out every day and get the observation of the wave heights from this website every day. So let's have a quick look at that one first. Okay. So that's this notebook here, Surf Report. We can open it up here. And this is the Surf Report feature pipeline. So if you're familiar with Python, you'll know that pip is used to install libraries. You need to install a library called Hopsworks. It will also need pandas and some other well-known notebooks or libraries such as NumPy, Request, and OS. So the first thing you need to do is decide if you're going to run it in backfill mode. And here we're not. So let's actually start this thing running. What am I doing? OK, we'll start running. And I set backfill to false. That means it's going to go out to the internet. It's going to go out to, we'll see the URL in a second, to download the page. So I'm just going to go through a little bit here. So where's the URL? It's encoded in here. Let's have a look, 1 second. OK, so this is the URL here, actually. So it's going to go in here. And what it does is it just scrapes the, you can see this is the surf report. It appears on the home page here. And you can see it was updated yesterday, and the height was 3 feet. So it's just scraping that data out of there. And let's go down here. How far have we gotten? OK, we'll run here, we'll run backfill false. OK, so you can see it downloaded 3 feet. Now you can see there's a couple of extra columns there, min height, max height, because sometimes they write a range of the heights. They don't always write just one value. So we have a little bit more data there. And the next thing we're going to do is, so this is a data frame. If you're not familiar with pandas, what we have now is a data frame containing the wave height, the max height, the min height, the beach ID. We've only one beach here, and then the time at which we observed this value. Now, the next thing we're going to do is just going to try and validate the data. So this is something you'll do in a production machine learning system. You don't want to write garbage in and then you get garbage out. So one of the things that you can do is you can use a library called Great Expectations. It's quite well known. And what we've done here is defined a rule in Great Expectations. So we're going to say that the wave height will be at least 0, the minimum value will be 0, and the maximum value will be 20. Now, waves can be higher than 20 feet, but not at this particular beach. So that's a reasonable amount. And then when we call the next cell, it's going to log us into the Hopsworks platform. It's going to get a reference to our feature store. It's going to create something called a feature group. This is a table with our features. And then we're going to insert this data frame that we got by downloading from the website. So you can see there's a couple of things get printed out here. The main thing at the end is that it runs a job to ingest the data. So the way it actually works is that it writes the data frame to the platform, and then internally in the platform, a Spark job will actually run, which takes 30 seconds to spin up, which will ingest the data. But what we can look as well at this point is the actual feature group or table of features that was created. And this was created quite a while ago, so we can see it here. Let's zoom in a little bit. So we've got 5 features, 20 commits. That means we've written to it 20 times. It's using 2 different training data sets, and these are the features here. And we can see there's a primary key here, the beach ID, and then the time at which it was observed is this what we call event time column. You can see where the feature group is used, and then here are the expectations. So when I just wrote the data right now, which is just right now, we can see the results. We can see the validation results. So the data that was read was correct, it was success, and you can get a report to make sure. So what you can also do, of course, there is you can have alerts set up that will send you an email or a Slack message if your feature pipeline fails. So you can define alerts here, and then you can search for the data. So once the data gets written, there's a bunch of other things you can do. You can preview the data. So this was the most recent value, but the historical values are all here as well. So you can get a preview of some of the data that's in here. And you can see this data is actually from 2004. You might want to also understand the data that was written. So what happens is, by default, descriptive statistics are computed over the data. So you can see, for example, the distribution of wave heights here. You see a very small number of them are 8 foot or higher. And we can also see, again, this is the wave heights there again. So a couple other things you can get is that if you have a lot of features in a feature table or feature group, you might have correlations between them. That means that maybe one of them is redundant. You can compute those automatically. And then you can see the history of what's happened here. So I just ran this notebook, and you can see it updated one row instead of inserting a new one because I ran this earlier. So it's just updating the value that was there. But you can see a history of what's happened. And I ran out of disk space, actually, on the platform. That's why that one failed. OK, so that gives us an idea of a feature pipeline that writes the data to the feature store. And this was the one that's writing our, what we said was the heights of the wave at the beach. There's another one here called the swell predictions feature pipeline. And this one goes out to the internet. It actually goes out to this website here at NOAA. I don't know if I have the URL for it, but we can see some of the data here, I guess. It'll download it here. OK. It's going to open LibreOffice. Not very nice. OK, but then you can see if we I had to zoom in here, but I'll close that. Basically, we have the period of the wave, the height of the wave, and the direction of the wave as the main features. And then we also have another feature called hits at, because we had to actually do some feature engineering. Excuse me. We had to estimate the time at which the swell, which these buoys are about 300 kilometers from the beach. So when a swell arrives at the buoy, it still takes a certain amount of time to reach the beach. So we had to estimate the time at which that swell would arrive at the beach, and we added that as an additional column there. OK, I'm not going to walk through this, but it's basically doing the same thing. It's building up a data frame. Our data frame will contain our features. We can see here the features are the height, the period, and direction. In this case, we have a lot more because we also are making predictions for the next 2 weeks. So we're actually going to have, I think, a total of 400 of them. And then we write them as a data frame to the feature store. OK, and then that ends up in here as a table of features. If we go back, so we have this table called swells exploded. And if we went through it, you can see, if I scroll all the way down here, you can see there's a lot of features. Because these features are the height at 38 hours, the period at 38 hours, all the way down to 236 hours. So there's quite a lot of features in there. OK. So there are what we call our feature pipelines. They're creating the features. And features, as you know, are the input data to models. They're the data that's used to train models, but also to make predictions. Because When we want to train a model, we're going to go to this feature store and go to these two feature groups and say, hey, I would like to train a model with this data. And then I create a model, and I'm going to store it back to the platform. When I want to make a prediction, I'm going to go back to the feature store and say, give me the latest data that's arrived, the latest feature values, and I'm going to use the model then that I download from the platform to make the predictions of the wave heights. So let's go to the next pipeline, which is, in this case, it's going to be the model training pipeline. So we can see here on this particular slide is we have, let's have a look here. This is our model training pipeline. Excuse me. Excuse me. So what we're going to have to do in the model training pipeline is we're going to have to read from something called a feature view. So in this particular platform, Hopsworks, the way it works is that features that are in this feature store, which is, you can consider it a data warehouse for features to be used for training and serving models, they're designed to be reused across many different models. So the way you do that is you basically select the features you'd like to use, and you create something called a feature view. It's a logical representation of the features. I say, these are the features I want to use for training and serving. And then from that, you can create training data, but you can also create inference data for batch predictions that we can do here. So that's what we're going to do in the next notebook. Let's have a quick look. Okay. So the training notebook, I think I had it open already. So this is our training notebook, and what it does here first is, we import our libraries as before. We log into the platform. I just ran this earlier. You can also apply what are called transformation functions. So in machine learning, when you have numerical data that's input to certain types of models. So if your modeling architecture uses gradient descent, then it often benefits from the features following what we call a normal or Gaussian distribution. So smooth values for your features. If you have some feature values which are much larger than others, the model tends to use those features to predict more than the other features. So what we want... Sorry. So what you often want to do is transform those numerical features. So you can do, in this case, we're using something called a standard scalar, which will normalize the feature values, the numerical feature values. In this case, the numerical feature values are height, period, and direction. So the direction can be anything up to 180 degrees. The height can be, it's going to be a small number between 0 and 3, and the period can be anything from 0 to about 14 seconds, 15 seconds. So you can see that they have different intervals. So it's better if you normalize the direction because the range is much higher in the direction than in the other features. So what we do is we have these transformation functions we apply to the height, period, and direction when we're creating this thing called a feature group, feature view, and this is how we create the feature view. We basically get reference to the two feature groups we created earlier. The one of the waves at the beach, the hinge, that's this one here, and then the second one is the predicted height of the open ocean swells at the buoys. So with those two feature groups, we basically say I want the wave height from the beach, and then I want all of the features from the swells feature group except the beach ID. And I join those together. So this is pandas-like syntax, and it gives me back this thing called a query object. Now, this seems like pretty straightforward code. If you're familiar with pandas, you're basically taking two data frames, you're joining them together. We haven't said what the join key is. In this case, the join key will be the beach ID, because there is underneath it, there's a excuse me. Underneath it, there's a query optimizer that's going to find the common join key between the two feature groups. But you can, of course, explicitly specify the join key if you need to. Now, what's happening in the background when we create this query which joins the features together, I'll get to it in a second, but it's doing something quite involved called a point-in-time correct join. I'll get to it in a second. So the query object contains the features we want, and then we create this thing called a feature view. And with this feature view, we can go ahead and create training data. So I can create training data as files, or I can get it back as pandas data frames. In this case, I'm creating files, CSV files. I'm saying 10% of the data will be test data. So I'm doing a random split of the data. And here I'm getting back my trained data files as pandas data frames. So I'm getting my train set, my test set, features and labels. And then we can go ahead and, oops, I didn't run this. Did I run this earlier? Okay, so I'll just skip over that. So what we can do next is we can apply our transformation functions. We can train our model. In this case, we're training k-nearest neighbors, and it's a classifier. So we're going to find the 3 closest observations that we've seen in the data set, and then we fit our model. So we're going to basically train our model on the input features and then on the training data set labels that we've encoded. Finally, then, when we've trained a model, we can estimate its performance on what we call the test set. So here we're using pretty standard scikit-learn metrics to evaluate the performance. So we can get things like the F1 score. And we can also get the RMSE score. Even though it's a classifier, you can also, it's quite useful in this case to understand the RMSE score, the root mean squared error performance. So once you've trained your model and got its performance, you can register it with the model registry, and now your model is in the platform. So all that's happening here is that you take your model and you use joblib to save it as a pickled Python object. You get the schema for the model from the training data features. So the input schema is the training data features, the output schema is the labels, and this is our schema here. And then we can pass in this dictive metrics. This is going to be saved in the feature store or in the platform where we can see them. So let's have a look at what happens after we run this. If we go up here. So we can see here then that I have a bunch of models here already. The surf one is down here. Let's look at the second version. So you can see here that it stored the metrics of the performance of the model. So I have the classification metrics and then this RMSE score. And we can see the just how to use that particular model. So this is a model registry. It's storing it, in fact, as files on the platform. So you can actually go ahead and look at the files themselves. Here we can see the pickled Python object and the sample data that we can use to test it, and then the schema. But how we're going to use this model is in something we call a batch prediction pipeline. Now, before I get to the batch prediction pipeline, I'm just going to talk about one complex thing that happens here in the background called the point-in-time correct join. So let's have a look at that. So here's one of the problems we have, that the surf reports are updated every 24 hours, but the swells are updated every 6 hours. So when I want to join the data together to create training data, I have to make sure that there's no what we call future data leakage. We don't want the swell height to be in the future, because otherwise the model won't be able to learn that. It'll be able to learn it, but then when it comes to get real data, it won't be able to predict correctly. So this was the code that we wrote to implement this, but what's actually happening in the background is that it's transpiling this simple Python code into very large point-in-time correct join SQL code that gets executed on the back end. And you could have terabytes of data, and because it's running on the back end, it'll run in Spark typically. Then you can actually join together huge volumes of data, even though you're only running simple Python. And the data, you might say, okay, I want this data back as files, and Python can, read in a terabyte of data and train a model. If you're using, for example, TensorFlow, it can do that incrementally. You don't need to have your data back as data frames. You can have it as files. But you can see there's quite a lot happening under the hood there for that. Okay, if you want to go along and try this, you can see Hopsworks AI is where you would need to create your account, and all you need is an API key that you can get when you call the login function there. Let's have a look at how we implement the serverless compute with GitHub Actions. So the only thing we need to do is we need to run these notebooks as Python programs, and they need to be able to write to the feature store the models, the features, and then even the predictions as well. So the way it's going to work is that in GitHub Actions, you have something called a workflow. And the workflow is this YAML file that we can see here on the left. Sorry, this one here. And obviously, it's a very caught down version of it. We can have a look at the actual file. But it has what you call a number of steps. And the kind of steps you have are, oh, please install Ubuntu, then install Python 3.8, pip install these requirements. These are the Python libraries you need. And then run this bash script. And you can say run it on a schedule, like run it once a day or every 6 hours. And all I do in this case is actually run a shell script. And the shell script looks like this. You can see it here. it's just going to take my notebook and convert it into a Python program and run it. So it's going to run sequentially from the top cell to the bottom. Excuse me. And that's basically it, right? So this is my production compute engine for the platform. For the training of models, we don't need to run that as a pipeline. You can run it when you need to. So if you want to do it really serverless, you could run it on Colab. But let's have a look at the inference pipeline, and then we'll have a look at the GitHub Actions. So the inference pipeline, this batch prediction pipeline here, you can see, what we wanted to do is take the latest predictions of the wave heights in the open ocean, and then output this image that we want to have with the wave heights. And also, it's going to write then the predictions back to the feature store, so we can do analysis of the predictions to see if it's performing well. So what we do is we basically log in to the platform. We download our model from the model registry. So this will download your model as a pickled Python object, because we saved it to the registry as that. And all we need to do is use joblib now to unpickle it. So you have to make sure now that the same version of scikit-learn, or scikit-learn in this case, is the same between training and inference. Okay, so once we have our model, we now need to get the batch inference data, and we do that with our feature view object. So we do call initialize on it. We did have some transformation functions. If you're very sophisticated, you'll know that transformation functions need state. They need to know the mean value of a given feature to normalize it. So the way we tell it that is by saying, well, this was the training dataset version that we trained the model on, and then it can go to the feature store and get those statistics, those training data statistics, to execute the transformation functions correctly. So then all it does is it goes to the feature store, it gets the latest prediction of the open ocean wave heights, periods, and directions, and then it's going to predict the wave height from that at the beach. So that's what it's doing here. It's just cleaning up the data a little bit, and then it inserts the predictions into a feature group so that we can do an analysis of it, and then we create a PNG file that we saw at the beginning, which is the actual output of the system. So when this program runs in my GitHub action, what's going to happen is it's going to run on the container, and it's going to save this file called latestlahinch.png on the container, and then my GitHub action will actually commit that file to the GitHub repo and push it. So that's happening in the GitHub action, and that's how the GitHub Pages page gets updated. Basically, my program creates the file, and then GitHub Actions will commit it and push it back into the repo. So last thing we'll look at is the GitHub Actions itself. So where are we here? Okay, back here. Okay. So we have these GitHub Actions here. And you can see I have this one called CJSurf report. This is the one that goes out to the Lahinch website and downloads the height of the waves. And you can see then when I ran out of disk space, I got a few errors there. And then the other one I run it actually more frequently. It's the one that predicts it takes the NOAA observations of the swell heights and writes them to the feature store. But in the same workflow, I actually also make the predictions. So after I've done that. So, so these two, they run on a schedule. Let's have a quick look at one of them here, because this is the more complex one. So this is the one that actually updates GitHub Pages. So we can see what it does is, we have this thing called workflow dispatch. That means you can run it from the user interface. Otherwise, it's going to run here. You can see here on this cron schedule. The steps are, firstly, we're going to use this GitHub action to push code back to GitHub. Then I'm going to install Ubuntu, Python 3.8, the requirements file that's in my repo. I set the Hopsworks API key. Then I create the swell predictions, get them and write them to the feature store. And this particular shell script will both write the swell features to the feature store, but it's also going to make the predictions. It's also going to run that batch inference pipeline. And then finally, we have this GitHub Pages action, which is going to just take this file, latestlahinch.png, and write it back to the repo. And that gets updated then on the web page. So that's it. If you're curious about this and you think this kind of looks interesting and you'd like to try something out like this, there is a course that's just started called serverlessml.org. I'm running it, and it's free, and everything is free on it. It's free to use this platform here. I'll just finish by showing you this is what one of our students did on the first day after the first lecture. So he built this system which takes it generates a flower called an iris flower, predicts what was there, tells you what was actually there, and then it does some complicated analysis of it. And then he has the recent predictions performance here in a confusion matrix to see how well that model performed over time. So you're doing a lot of monitoring, not just the full end-to-end, but also understanding the performance of your model in this. So that's it. Thank you.